Hello everyone. Today we're going to be discussing dependent motion. In this video, we will go over the definition of dependent motion, the purpose of using dependent motion techniques, some examples of real-world applications of dependent motion, and lastly, we'll go over a few examples of problems that you may expect to see in your homework and some strategies you may find useful in not only solving the problem, but most importantly, understanding why dependent motion techniques best describe the scenario. Dependent motion is any time the motion of a particle is directly related to the motion of another particle. Using these techniques, we can analyze certain systems to determine the relationship between acceleration, velocity, and the displacement of two particles. The most common real-world applications we can expect to see examples of dependent motion are in crane and elevator systems, as they mechanically operate using the same basic principles of pulleys. We will now look at the first two examples of dependent motion and examine a strategy on how to first understand the problem and then ultimately solve it. When approaching a problem that requires dependent motion techniques, it may be best to break the analysis down into the following 5 steps. Step 1. Set datum lines. Identify points of the system that will experience no change in position. Draw datum lines perpendicular to the lines of motion. Varying complexities of the problem may necessitate multiple datum lines. Choosing proper datum lines allows us to treat the scenario as a rectilinear motion problem, which specifies the kind of calculations we can expect to be doing. Step 2. Set S position vectors. Identify elements in the system that will be experiencing motion and denote them with an S designation relative to the element they are describing. Step 3. If necessary, use lowercase letters fixed to fixed distances. Some distances beneath the datum lines will remain stationary and can be denoted with a lowercase letter. Examples of extraneous elements can include lengths of rope wrapped around the pulleys. These elements can be ignored. Step 4. Form a symbolic equation for the system. Vectors and the fixed distances can be additive or be used as the legs of a right triangle to describe the system. We can set these elements equal to the totality of the system, L in the case of a rope. Step 5. Take the derivative with respect to time of the equation. Now that we have established a symbolic representation of the element position with respect to time, we can take the derivative to find the object's velocity. If we take the derivative with respect to time again, we can also find the acceleration. In our first example, we see that block B is attached to a smaller pulley that is in turn suspended from a larger pulley that is secured to a horizontal surface. A rope is wrapped around both pulleys as is shown, with one end left unsecured. The problem asks us how we can determine what velocity the block will travel based on how fast point A is pulled downward. Our first step in solving this problem is to identify which element of the system will be experiencing no motion. We do this because these elements can be described as a constant and do not need to be included in our analysis of the motion of the block. Once we have identified which elements of the system will remain constant, we will draw a datum line to mark the boundary between moving and non-moving elements of the system. This is useful as it will help in referencing where the points of interest may be located in our system. A vertical line will then be drawn downward from the datum line to indicate the positive y direction. Now we will examine the moving elements in our system. We see that below the datum line are 4 lengths of rope separated by the pulleys. The furthest length to the left is denoted by point A, and as the length of the piece of rope will change, we'll refer to it as S of A. If we were to draw a free body diagram of block B, we would find that there are 3 cables where the tension forces act on block B. As we can expect all 3 of these cables to experience motion, we will refer to all 3 of the cables as S of B individually. It's important to note that the same vector can be used for equal lengths. While performing your analysis of the system, it is important to note the extraneous elements of your system. This can include unchanging distances below your datum line or the pieces of rope that are actually wrapped around the pulleys. You may denote the unchanging distances with a lowercase letter. The lengths of rope wrapped around the pulleys can simply be ignored. Now that we have identified the individual elements of the system, it is best to take a step back and look at the system as a whole. Once we do so, we can observe how the entire system is using only a single piece of rope. We can model this by representing the entire length of the rope as the letter L. At this point, we have successfully analyzed all of the relevant elements to our system and can begin our calculations. The elements in Step 2 and Step 4 work to describe the same physical object. As such, we can set these elements equal to each other. Once we do that, your equation should look like L equals S of A plus 3S of B. Previously, we had learned that if we take the derivative of position with respect to time, we will determine velocity. Applying this to our equation will result in 0 equaling v of A plus 3v of B. As length was constant, it became 0 after taking the derivative. Assuming that we were given the velocity of A, we can now use algebra to determine the velocity of block B. Given that we were told that the velocity of A was constant, we can use this to infer that the acceleration in the system is 0. This concludes how to solve our first example. For the purposes of better understanding dependent motion, a practical model was constructed. In the video, we can clearly see the relationship between the position of the tag on the rightmost length of rope and the position of the orange indicator hanging from the lowest pulley, as whenever the tag was lowered, the indicator would then rise.
For angled blocks that remain in contact with each other, one block can only move as much, as fast, or accelerate as quickly as the movement of the other block allows. The amount that block B can move is limited by the amount that block A moves and vice versa. Their movement is not equal, however. Rather, it is proportional based on the angle they are sliding against each other at. The block that is moving in the direction of the longer leg of the right triangle formed with the slant as hypotenuse, that is to say, the slanted angle that they're at, the one that is along the longer side of that triangle has to move further. Must move further than the block that is moving in the direction of the shorter leg of that same triangle. This is useful because when you do the force analysis of the problem, you are left with three unknown variables: the normal force between the blocks and the accelerations of the two blocks. And you only have two equations, the two force equations that contain the block accelerations. The third equation needed can be obtained through the application of dependent motion in the form of the proportion between the accelerations of the two blocks, where one of the accelerations equals the other times the tangent of that angle between them.
We will now show how the steps described earlier can be used to solve this problem.
Step 1. Set datum lines. First, identify the non-moving point or points. The corner that connects the wall and the floor is fixed at the extreme end of each block's movement. Second, draw datum lines. You need one for each block because even though the respective datum lines will pass through the same point, the lines of motion, and thus the datum lines, are going in different directions. Step 2. Set S position vectors. First, draw a right triangle with the right angle at the non-moving point and where the legs are pointing perpendicular to the datum lines and towards one of the blocks. In this example problem, the blocks are the element of interest. The hypotenuse should intersect with the horizontal leg at the angle theta, which is the same angle as is between the slant and the horizontal direction. The legs of this triangle are the position vectors. Step 3. If necessary, use lowercase letters to fixed distances. No fixed distances are needed to be represented in this problem. Step 4. Form a symbolic equation for the system. For a symbolic equation equating the position vectors to the total distance of the block from the datums. Step 5. Take the derivative with respect to time of the equation. Take derivatives with respect to time, resulting in the final equation needed to solve the problem, as is shown.
Here is a brief physical representation of these concepts at work.
This concludes our presentation on dependent motion. Our team for this project consisted of Joshua Warren as the team manager, Joseph Ray as the team scribe, and Thomas Truitt as team editor. For more information on this topic, you can either message us personally through Canvas or read through Chapter 12, Section 9 of your book. We hope this video was informative. Thanks for listening and have a wonderful day.